I apologize for that interruption. Okay, here is vectors part 2. So what we're going to do is resolve each one of these vectors into its x and y components. I'm hoping this will give you a better feeling for how things go with the mathematical reference system and just with the trigonometry involved. So first, let's look at A, and I recommend that you draw this out with me as we go here. So the first thing that you do is sketch an XY coordinate system. Then you draw the vector in. Now you could draw this into scale using a ruler and a protractor, or you can just make a representation. And always draw the vector with the tail of the vector at the origin of the coordinate system. So there's a representation of my vector A. 60 meters at 120 degrees. That's 30 degrees past 90 from the x-axis. Then you dash a parallel line, that little pink one right there, over to the y-axis, parallel to the, I'm dashing it parallel to the x-axis. Now I'm going to dash another one parallel to the y-axis down to the x-axis. That defines a rectangle, and our vector is now the diagonal of that rectangle. The components are the sides of the rectangle that are along the axes. So the y component is the vertical side of the rectangle, the x component is the horizontal side. And now you use the relationship, the x component equals the length of the vector, 60 meters, times the cosine of the angle, 120, and you get negative 30 meters. The y component is 60 meters times the sine of the angle, or 52 meters. I would like to caution you to make sure that your calculator is set in degree mode and not radian mode. Okay, vector B. Start out the same way. Sketch the coordinate system, then sketch the vector. So 225 degrees, that means we're down in the third quadrant, 45 degrees past 180. So this angle right here, which is often called the reference angle, is 45 degrees, and 225 is the total angle from the 0 degree direction. I know it's weird to think about angles that are beyond obtuse, but that's what we're going to do in this section, actually whenever we deal with vectors. So you just need to expand your definition. So once again, I'm dashing in a segment parallel to the x-axis and parallel to the y-axis. That defines my rectangle, and my vector that I'm resolving into components is the diagonal of that rectangle, and in this case, of course, it's a square. So there I'm drawing in the x component and the y component. They follow along the axis and are defined by the sides of the rectangle. Now I'm using trigonometry. B sub x equals B, 40 meters, times the cosine of the standard position angle, 225 degrees, and it's negative 28.3 meters. Your calculator should give you this result, so that's something you need to practice. Make sure you can get this result with your calculator. And by is 40 meters times the sine of 225, negative 28.3 meters, also negative. Okay, so what I want you to do is look at this problem, and using the components of this displacement vector right here, I want you to see if you can answer these questions that follow. So this one says you fly east in an airplane for 100 kilometers. You then turn left 60 degrees, so that means you're up 60 degrees north of east, and you fly 200 kilometers. How far north of the starting point are you? So you can pause the video and see if you can give me an answer to that. And you should have gotten 170 kilometers. So what's going on there is you want the y component of this 200 kilometers at 60 degrees vector. So that's what you're finding. Now, the next question is, how far east of the starting point are you? So you can pause the video and then answer it. And I don't know if you put 200 or not, but once again, you're looking at the component of this vector, and if you go 200 kilometers at 60 degrees, then your x component is going to be 200 times the cosine of 60, and 200 times the cosine of 60 is 100, so you're going to have 100 plus 100, or 200 kilometers. Okay, now in general, okay, wait a minute, sorry. Okay, in general, you're also going to need to be able to go backwards. So in addition to being able to find components, sometimes you're going to need to go to the r theta notation, which is magnitude and direction, when you're given the components. So here are the two principal forms that we're going to use. Remember, a vector has two parts, magnitude and direction. And what we're going to do is we're going to go back and forth from components, x and y components, east and north components, however you want to look at it, to r theta, which is magnitude and direction. So there are equivalent expressions, one in terms of the coordinates on the Cartesian coordinate system, and the other one in terms of the length of the vector and its direction. So here are the rules. You always get the magnitude of the vector if you've got the components using the Pythagorean Theorem. You should recall that from junior high or high school. The sum of the squares of the legs of a right triangle is the hypotenuse squared. I hope I said the sum of the squares of the legs. So it's a squared plus b squared equals c squared. In this case, d is equal to the square root of d sub x squared plus d sub y squared. Now, so it's pretty easy to find the magnitude, right? It's just the Pythagorean Theorem. It's a little trickier to find the direction, and this week in lab we're going to do, I think it's this week, it might be next week, we're going to do a lab that helps you practice this vector addition. So finding the angle is a little trickier. I always recommend that you find the angle called the reference angle, which is the acute angle in the quadrant where the vector appears. And then once you get this reference angle, you should translate that into the standard position angle. So in this case, since it's in the fourth quadrant, it would be 360 minus whatever this angle is. But to find the reference angle, you're going to use arctangent, which is tan to the -1 on your calculator. So it's usually the second tangent function. So you want the arctan of the y component absolute value of it divided by the absolute value of the x component. You don't want to pay attention to the SIGNs of the components in this stage. That's why I've drawn the absolute value symbols around the dy and the dx. We're going to do an example of this. Okay, so here's the mechanism. You sketch the x and y components in the proper direction, once again emanating from the origin of the coordinate system. Use the Pythagorean Theorem to compute the magnitude. Use the absolute values of the components to compute the angle alpha. It's called the reference angle. It's the acute angle that the resultant makes with the x-axis. And then calculate theta based on the quadrant. There are different rules for each quadrant. Okay, when calculating the angle, here I've broken it down for you. Use the absolute values of the components to calculate alpha. Compute C using the inverse tangent. Compute theta from alpha based on the quadrant. And so, there you go. Alright, let me go back to that. So, I've got the rules for each quadrant here. You may want to write those down, or at least know where to reference this slide, because you're going to need to be doing this frequently.